And kinetic energy, as I mentioned last class, the energy related to motion. If only the change in system is the speed, so if there is no change on height and there are no springs or anything acting on the body, then we have the work energy theorem, right? Where the change of kinetic energy is equal to the work. Now, remember, that work is due to an external force. So we can use both concepts to start analyzing more complex systems. The idea that the energy is conserved, and then the energy at some point will be transferred to another point, and they are equal, which is actually what we use in planetary motion, for example. We say that because it's vacuum, there's no friction, no air. So the Earth goes around the sun by conservation of energy and momentum, and angular momentum. And from that point, we can actually start getting the whole idea of the orbit of the Earth around the sun. But on Earth, we have systems where there can be a work due to an external force, that's your W there, and that will produce a change of kinetic energy from initial to final speed. So I'm going to answer these questions to do it very quickly. So if you have a block sliding in a horizontal surface with friction, and even if you ignore sound, this block is in a non-isolated system, right? As I said, there is a external force. That friction will make the block lose energy. So it's non-isolated, right? The friction produces some sort of work against the motion. If now you have, again, you have friction, and even if you ignore sound, you still are in a non-isolated, right? The only way you're going to have isolated is if you have the block sliding in a horizontal surface and you ignore any sound, and if the system, wait, is this? Here I think we should have put ignore the friction as well. So if we ignore the friction and the sound, they were in isolated, so I have to correct that question. Okay. So this one, I mean, this is more related to overall system where you have heat, matter transfer, electrical energy, electromagnetic radiation, mechanical waves. You are going to eventually study all that, right? But just as it says there in the slide, the change in the total amount of energy in the system is equal to the total amount of energy that crosses the boundary of the system. So whatever is passing through the system is equal to the change of the total energy. So, I mean, it's easier than what it sounds, trust me. Especially when we do the problems, you will see that in mechanics, we don't have to worry much. We just have to determine which points we are focusing on. And if we have potential energy, we have to look at the boundary. We have to look at the reference point, all right? So that's that. So when using the conservation of energy, you have to know and define the system, identify the beginning and end. So you have to identify the beginning and end of the points of interest, well, the same initial and final configurations, and what type of energy are acting on each point of the system. Right, so that's basically a summary of that. So we got this, and this, and this. Okay, so let's start with examples. You have a book from some height, you let it go, isolated, so we're gonna ignore air friction, sound, and then you wanna find the speed of the book at this position. So we have done this problem with kinematics, but start doing these problems now in a more general way, which is using energy, right? So if we have, so I'm just gonna use the ground is going to be your reference this problem. You have a mass from certain height, which is called y initial, and then it's gonna drop due to gravity. So gravity is always acting, right? And it's going to be here now at certain final position. We're gonna find the velocity here. Now let's say this is a rest. If we have a problem like this, the first point of interest is here. So this will be your point A. And this will be your point B. Now, I'm going to say that the mass has mass M, but you will see that in many of these problems of conservation of energy, the mass won't matter, especially if you have only kinetic and potential energy due to gravity. So conservation of the energy at A is equal to, if we do it with respect to this is going to be my reference. Just the potential energy because it's at rest. The energy at A will be the mass times gravity times height, which is y final. Here is 0, right? So your reference point is your 0 point. For B, the potential energy is now with YF, but there is some speed. So it's now M G Y F, it should be Y initial, plus the kinetic energy. So what I'm doing is I'm writing the mechanical energy here. Now, because we are in the whole, or not just because of that, but because because we are ignoring any sort of external forces except gravity, which is conservative, we can use the conservation of energy, which is that energy at A is equal to energy at B. And that's how we find the speed, V. So mgy y initial is equal to mg y final plus 1/2 mv squared. You can send this to this side and factorize mg. So you have mg y initial y final equals to 1/2. Look, m and m cancels. So here, right, the velocity, the speed will be the square root of 2 times gravity times y initial minus y final. If you use kinematics, you will have the same equation. But of course, the problems are going to be more, not complicated, but more complex. There are more complex situations, like what I was mentioning last class, the roller coaster, where we have to be careful with the potential and kinetic energy and our reference point. So that's basically the summary of how you solve a problem or a situation using the conservation of energy, right? You first check for the initial and final point, and then you write down the mechanical energy at the initial and final point, and then you set them equal to each other. Now, let's take a look at this. There is a question in the slides that says you have a rock with mass m and another rock with mass 2m, and you drop them from the same height. Which one will have the highest kinetic energy as they strike the ground? So we already know from Newton's laws that regardless of the mass, they will both reach the ground at the same rate, the same speed, the same time. So in terms of the speed, they will have the same speed. But because one is more massive than the other, the kinetic energy of the more massive rock will be greater than the kinetic energy of the less massive. But we can also use energy to show you that if you have different masses, or if you're launching, as I will show you later, a mass, right? It doesn't matter, you will have the same final speed. So if we have here the ground, and you have here mass m, mass 2m, on the same height. This will drop here, and this one will drop. They both will reach the same velocity. Right, because if I do it here, for example, the energy here respect to the ground, energy initial will be 2m g h. The energy final will be 1/2 of 2m squared. If I set them equal to each other, m2 when you get the same square root of 2 same speed. But the kinetic energy is mv squared. The kinetic energy here the kinetic energy here will be 1/2 mv squared. Same speed, but different. So a typical problem with a spring is this. You have the ground, and you're gonna have a platform, and it's attached to a spring. And yes, you're gonna have a max that you're gonna drop. When you drop, the initial speed is 0. The constant of the spring, I will make it 250 newtons per meter. And you want to find a few things. If I give you the height, let's make it 12 meters. What will be the speed here? I want to find the speed here. And what will be the maximum elongation of the spring? Because as the mass lands on the platform, this will elongate to a position. So you want to find the maximum compression. So there's 2 parts. Find the speed there. Okay. Find the maximum compression. Okay. To find the speed, don't make the ground in this problem, again, like the previous one, I won't make the ground my reference point. Because if I make the ground my reference point, I have to know the natural length of the spring, and they don't give me that. Right? So let's make for part A reference here, where the object on the platform. I also don't have the mass of the ball. It's fine. So for part A, this will be my final position, and this will be my initial position. Only gravity is acting on this problem, this system. So it's only a conservative force, so perfect. We can use conservation of it. We're ignoring air resistance. So energy at A is equal to energy at B. All right. Since you are dropping the mass, the only energy is the potential energy due to its height, since that's my reference point. So this will be mgh. That's equal to the energy at B. Since that's your reference, no potential energy, just kinetic. See? So it gets more simplified, or simplified, and then 1/2 m and mass, it's cancelled. So 24 times gravity is equal to V squared. Then the value of V will be the square root of that, which, let's see, 15 meters. Right. That's part A. What about part B? I want to find the maximum compression of the spring. For part B, now you want to make a reference point here. And the maximum x is when the mass platform system is at rest, stops. Right? At the instant it stops. So, since we can use conservation of energy, this will be now my position C. Energy at A is equal to energy at B is equal to energy at C. Yeah. Energy at A is equal to energy at B equals to energy at C. Now, in many problems, or I've seen this problem where they don't ask you this. So you have to be careful because now, since that's your reference point, the energy at B now has some potential. So I normally suggest students, when they want to do the maximum compression on this problem, focus on the initial and the final. Don't use the intermediate step much because since we changed the reference, the energy at B won't just be kinetic. You will include some potential due to X. So let's just use the initial, which is this. But now my reference point is this. So since now we have the platform going down some value X, the potential energy at A is actually the mass times gravity times the height, which is 1 plus X. And the energy at C will be 1/2 the constant of the spring times X squared. Now, for the second part, you will need a mass. So we need to add that for this part. So let's put here, assume M to be, let's make it 5 kilos. We didn't need it for the first part because it canceled. For this one, we need it. So that's the equation. Now, where does the plus X come? Because remember, now this is your reference point. So you need to add this. All right. So I can erase this. We already did part A. We go and put it there. 5 times 9.8 times 12 plus X equals to half 5 is 50. So 9.8 times 12 times this. Let's get to that. 117.6 plus 9.8x equals to 50 divided by 2, 25. The quadratic equation will be well, we have to just use the quadratic formula. It's physics. We cannot have negative values of length. So we just take the positive. X will be minus B plus or minus. We can look. B squared minus 4A C. C is negative. over 2A. Let's take a look at the square root, and that will indicate if we use a positive or negative solution. Most likely the positive. 9.8 times 96. So 100 times 6. 108. We cannot use a negative. That's all one. The square root of all this is 108. We have to use a positive, so plus divided by 50, 2.4. So X max equals to 2.4. All right. Another classic problem on conservation of energy. No conservative forces, a mass drop towards a spring with a platform attached to spring.